for the most part, at least the last one, is a modeling effort that uses IPCC scenarios to address ecosystem sensitivities and study interaction and feedbacks between different variables. And without further ado, then I will pass the control to you, Mike and Kirsten. Thank you so much for your time.
Thanks, Guillermo. So today, my name is Mike Sigler, and with Kirsten Holston, we're both with NOAA's Alaska Fisheries Science Center. I'll first describe the Regional Action Plan for Climate Science in the Southeastern Bering Sea, and then Kirsten will dive into some detail, more broader description, deeper description of one major part of the Regional Action Plan, that is the Alaska Climate Project. The goal for NOAA, well, National Marine Fisheries, was to implement a climate science strategy, and there's both a national document as well as now regional action plans for all the regions of the country, from the Bering Sea in the north to the Gulf of Mexico in the south, Caribbean in the south. And then the purpose of these regional action plans are to identify specific actions to implement the climate science strategy in each region over the next 5 years, and then to build awareness, support, and partnerships to help meet the core needs of this science strategy. We in Alaska view the regional action plan as a three-legged stool consisting of and being built on ecosystem monitoring, and then doing work to identify mechanisms like the integrated ecosystem research programs that have been funded by North Pacific Research Board and others, and completed by NOAA and others. And then the other leg of the stool is modeling, for example, what Kirsten will describe. And together, these three-legged stools are paired together, triad together to inform climate-informed management. This is both fisheries, which are very important in Alaska, as well as protected species, i.e. marine mammals. I'll give examples of each leg of the stool. For example, for monitoring in Alaska, this is for the southeastern Bering Sea. We have seasonal surveys, for example, an oceanographic set of oceanographic stations along a depth contour of mid-shelf of the southeastern Bering Sea, larval surveys, age zero surveys later in the year, and then our major surveys to survey adults, which then you can track basically year classes, cohorts of fish species and crab species through their life. We also display this monitoring through Alaska Marine Ecosystem Considerations, which doesn't just cover fish, but also covers zooplankton, things like fixed-billed murre, reproductive success, so it's ecosystem reporting indicator reports. A very comprehensive effort led by Stephanie Zador at the Science Center. We also identify mechanisms. One example of that is ocean acidification research. For example, in the Kodiak Lab, Kodiak, Alaska, Bob Foy leads an effort there to identify effects on important crab stocks in Alaska. Then he works with modelers at University of Washington and in Seattle and Alaska Fisheries Science Center, myself and Andre Punt, to make forecasts of what's going to happen to those species. Things don't look good for red king crab if ocean acidification manifests itself fully. We also identify mechanisms for marine mammals, for example, trying to understand the decline in pup production at Pribilof Islands, using tools like satellite telemetry, understand winter migration, summer foraging, and then link. And this is also another modeling project pairing field data with model results, Jeremy Sterling and others, to link fine scale changes in first scale foraging behavior with prey distribution. A major modeling effort is the Alaska Climate Project, which Kirsten will describe. So I'll leave it there. We also then report and try to explain how these potential changes in climate effects on fisheries will affect communities And you can see here one of those studies that explains how climate effects will affect coastal communities around Alaska, anywhere from yellow caution flags to red warnings for some smaller coastal communities in Alaska. Kirsten will talk about the Alaska Climate Project. So please go ahead, Kirsten.
Okay, just going to go ahead and test my audio. Can everybody hear me okay?
Yes.
Great. So yes, I'm one of the co-PIs and lead PIs on the Alaska Climate Change Integrated Modeling Project, which we call ACLIM for short. But it's actually a team of about 10 different experts that have come together following the Bering Sea Integrated Research Project that was funded through the NPRB, North Pacific Research Board. And so we've taken that initial work that was done through this integrated project, which provided a lot of the understanding of the mechanisms for how bottom-up and top-down controls influence the Bering Sea ecosystem. And now we're trying to roll that forward to really evaluate climate change impacts on the Bering Sea ecosystem all the way up through fisheries and fishery-dependent communities. Okay, next slide. So this is a team of collaborators that involve everybody from physical oceanographers through the Pacific Marine Environmental Laboratory and the University of Washington. We have a number of stock assessment modelers and food web modelers in the team. And we also have 3 socioeconomic modelers as well. And so the idea is to couple what sort of has spun up as individual models together in a collaborative effort. Next slide. And there's 2 main focus, focal points of ACLIM. It's a pretty ambitious project. We're about 2 years into 3 years of support, although we're hoping for a bit more support. The first is how might the Bering Sea change? So this is projecting changes in species abundance and biomass and distributions, and tracking how that might change catch, for example. But really the focal component of ACLIM is to do a management strategy evaluation to understand how our fisheries management that as it currently exists will perform under future conditions. And so part of it is to understand where we're going, but a large part of it is to sort of do a stress test on our existing fisheries management. And then also with the collaboration with the council and stakeholders, evaluate alternative management strategies if those are needed. Okay, next slide. So the background to this is that we have 30 years or so of data where we've been monitoring the ecosystem, we've been monitoring physical conditions, and a mechanistic understanding of how those changes in sort of physical conditions in the Bering Sea translate into changes in productivity, which translates to changes in fisheries and then ultimately fishing communities, has really emerged again out of these integrated projects. So this is an example. This is a shot of the summer over the Bering Sea. Each year there is one of the panels. And the blue there is something we refer to as the cold pool, which is this memory of sea ice, winter sea ice that was over the Bering Sea and sort of remains there. This cold water remains there during the summer. And this cold pool, of course, mitigates predator and prey interactions because some species will enter the cold pool and others won't. But it's also an indicator of productivity in the system. And so we can use indices like these. For example, this is one that gets reported in those ecosystem monitoring reports that Mike mentioned. And we can then link those up to biological models. We can reproduce this cold pool. I'll show you that in a moment using physical oceanography models. And then we can project that forward under global climate models. And that's the idea behind ACLIM. Right, next slide. So what we start with, if you look in the upper sort of left-hand panel of this image, is we start with a series of global climate models. And we picked multiple global climate models because one of the things that came out of our previous work was an understanding that the global climate models behave very differently in the Bering Sea region. And so rather than just pick one GFDL model, for example, we picked a suite of them. And we've tried to select models, and I'll talk about that in a minute, that sort of ranged from colder running models to warmer running models, because again, we want to test our management scenarios under these different futures. And then we take those global climate models. We have a couple of different future carbons, sort of future carbon scenarios, one from the IPCC AR4 and then two from the last IPCC assessment report. And we run those forward through a coupled oceanographic and nutrient zooplankton model. And so that's, you can see Mike's mouse there, that's that one there. And the reason we do that is because the global climate models don't reproduce all of the features that we need in the system that we think are important, like that cold pool. But this downscaled ROMS MPZ model does a pretty good job of reproducing those features, those oceanographic features that we think are important. And as part of the ACLIM project, we've then taken those projections, which can be, they're three-dimensional in space and they're weekly, and we further pull indices and connect those models then to coupled ecological and socio-economic models. And that's sort of this integrated picture down at the bottom here. And I should mention that this work is funded through FATE. It's a joint funded project through FATE, Fisheries and the Environment, SAM, the Stock Assessment and Analytical Methods Program, and also S&T's Climate Regimes and Ecosystem Productivity. But it's heavily leveraged through the work that was done as part of the Bering Sea Integrated Research Project and also our NOAA's Integrated Ecosystem Assessment Program, which does the upkeep of a lot of the models. Okay, next step, or next slide, sorry. So this is the general idea. We're trying to trace the cascade of uncertainty and projections all the way through our projections. And so ideally, when we come out of this at the end, we'll have a set of fishing scenarios and we'll have a set of climate scenarios, and we can say, this is not only the direction that maybe fisheries or a species population is going, but here's the estimate of certainty around that. And to do that, I mentioned we have the suite of 11 future climate scenarios. Next slide. And we've selected climate scenarios and global climate models that span a sort of behavior of predicting or projecting sea surface temperature and precipitation in the Bering Sea. So their first cut was to make sure the global climate model in hand reproduced features like the right timing of ice melt and the duration of spring windows of bloom. But once we eliminated ones that weren't performing well on that aspect, we then selected models that spanned sort of a range of taxonomies, if you will, for models. And this is actually from Neti et al.'s recent paper showing the different models that we are using in our suite, GFDL all the way down to MyROC. And so some are more similar than others. Okay, next slide. Then we also selected 3 future carbon emission scenarios. We had the CRES A1B in hand from our visitor era, and then we additionally selected the RCP 8.5, if you're familiar with that, which is sort of business as usual carbon future, and then RCP 4.5, which has a more aggressive curbing of carbon emissions by mid-century. I think an important point is to note that there's not divergence in any of these until around 2030 or so. Next. Once we had those climate scenarios, we then have been plugging them into a suite of biological models, and we have sort of 5 types of biological models, although there's a number of different individual models for each species. Starting on the left-hand side, we have climate-enhanced stock assessment models. These are age-structured models. They're essentially the stock assessment models we use now, except that there's usually a climate driver, a linkage between climate and recruitment, for example, or climate and growth. And then sort of moving from left to right, we have climate-enhanced multi-species models, climate-enhanced food web models that include EcoPath with EcoSim, the size spectrum model, which we're building as part of this project. And all the way on the right, we have a spatially explicit, high temporal resolution end-to-end model where fish dynamics are actually embedded in that ROMS MPZ grid. And so this allows us to evaluate how important assumptions about trophic interactions and indirect pathways might be to changing projections or or the sensitivity of those projections to those assumptions. And then finally, for each of these biological models, we're running a series of fishing scenarios, and we've identified 8 fishing scenarios thus far. We're going to start with, for example, status quo. So reproducing what we do now, how does that behave under future climate change? We're going to present that to the council in the fall. And then with council feedback, we're going to evaluate a variety of other potential scenarios that range from things like maximum sustainable yield, maybe a more conservation-based approach, a no fishing scenario, bycatch scenario, et cetera. And those then will be evaluated for their sensitivity as well. One of the things that's emerging is that fishing pressure is a pretty strong lever that we can pull and push in order to absorb or attenuate some of those climate impacts. Okay, next slide. So our progress to date is we've completed the downscaling. We've developed some data visualization tools. A big challenge with this project is actually just getting the data in a format that everybody can use and share. And so I think we've tackled that. We've scoped our bioeconomic fishing scenarios, and we've done a series of outreach and feedbacks, iterative feedbacks with council members and stakeholders. Next step, next slide. So now I'm just going to briefly show a little bit of what these projections look like. This is summer bottom temperatures for the Bering Sea this is actually from the groundfish survey in the Bering Sea that takes place every year. And just to highlight, in 2016, it was the warmest year that we'd observed in the system at 4.5 degrees, and those bars are the standard deviations around the mean. Okay, next slide. And then the red line here is the model's replicated survey bottom temperatures. So we go out and sample the model as if we were surveying the system. And as you can see, the model, which is in red there, does a pretty good job of reproducing those bottom temperatures in the system. It does run a little bit cold because it holds on to ice a little bit longer, but overall it's reproducing, that hindcast is reproducing what we saw in the system pretty well. So we then take that model and we run these projected global climate models through it. So it forces the boundary conditions of the model. Next slide. And again, we do this under, and I was just going to mention that it also reproduces the spatial extent of that cold pool very well. So on the left is the data, and on the right is the model reproduced summer bottom temperatures. Next slide. So we run the model forward under conditions that look a lot like we've seen in the system in the past. We still have warm and cold periods and sort of these stanzas of warm and cold conditions, but no trend. And then also scenarios where, go ahead, next slide, where things increase pretty dramatically. This is actually under the MyRock global climate model under our 8.5. And then you can hit next slide a few times, Mike. Yeah, one more time there. And then a whole suite of maybe one too many, a whole suite of models in between. So we get this ensemble of projections. Okay, next slide. And this is just a screenshot of one of our data explorers that allow us to evaluate different models very quickly. We can flip on different, for example, here we have bottom temperature, or we can load zooplankton abundance, and we can flip through the different models and projections pretty easily. Next slide. And so these are screenshots of some indices that are emerging as sort of interesting and important to the biological models. So bottom temperature under 4.5, this is the most conservative carbon future, and 8.5, which is a more business as usual carbon future. And this is bottom temperature from the ensemble on the left and on the right. And as you can see, there's a difference there in the bottom temperature for the Bering Sea in the summer. Next slide. There may be slight differences in projections of spring zooplankton with a little bit of an increase under 8.5. And next slide. And importantly, fall zooplankton decreases pretty dramatically in these 8.5 scenarios. Fall zooplankton, we think, might be an important component of overwinter survival for a lot of fish in the system. So getting this last burst of food right before they go into the winter could be very important. Next slide. So what we do is we take those indices, we couple them to biological models. Next slide. And socioeconomic models. And I won't go into much detail. There's different ways to couple that. You can do it through recruitment, growth, predator-prey overlap, distributions, etc. Next slide. But in the end, what we're hoping to get is something that looks a little bit like this, where scenarios might be different management scenarios or harvest scenarios, and then there's some estimate of the range of projections around those future projections. And so this would be a tool to allow, say there was a risk threshold or a cutoff that could be used to evaluate the probability of exceeding that threshold. Next slide. And all of this is taking place sort of on the right-hand side. This is really, I think there's just this slide and one more and I'll wrap up. This is all on the right-hand side of this image. This is a nice paper, a figure from a nice paper by Desiree Tomasi that came out earlier this year. And this is sort of the time scale and space scale and the different, the sort of role of different forecasts and projections to informing management at those different levels. And we're over in these longer term forecasts. It's really strategic planning, trying to understand where the system is going, but also there is a bit of feedback that comes into the middle, sort of that yellow bubble there, which tells us how much, how sensitive these future scenarios are to things like biological catch limits. So an important part of this, next slide, is the feedback between these long-term projections and these short-term ecological forecasts, and we're working very closely on those. Next slide, this is the last slide. Just to say that the challenges we've face these sort of collaborative efforts are things like those global climate model selections, the computing capacity limitations is a huge one, data sharing and model coupling, so both internal data sharing and sharing with the public, and evolution of models to incorporate nascent science. So it's really important to keep these models up to date and ready to sort of bring in new mechanisms. I think we have great success to date on a very aggressive timeline because we have a strong integrated research program here at the center. So field information works its way into the models very quickly. We have the right mix of people and tools. We have engagement with council and stakeholders, which is iterative. And again, these long-term analyses are coupled with these short-term forecasts. So we're learning from both efforts. And that's all I have. I'm sorry I went a little bit long on that.
Thank you so much, Kirsten and Mike, for such an insightful presentation. Is there anyone who has questions for Kirsten or Mike?
Yeah, Guillermo, this is Francis, if I can ask a question.
Sure, go ahead.
Yeah, hey, Kirsten, thanks a lot for that. That sounds a really exciting and challenging project that you guys are working on. And I was wondering if you could talk more about the comparison of those 4 biological models that you have there running and coupled, and how you're thinking about comparing their outputs.
Yeah, actually, it's it's still open for input because we're actively discussing it. One of the things that sort of emerges from all of these models is the common currency of biomass. And so the first place we're looking is what's the change in biomass of the species that are sort of included in all of those models, and why are there differences? And so some of the things that drive those differences are those predator and prey interactions in sort of non-intuitive ways. And so if you fish a predator harder, you may actually release some species from predation, and then that leads to higher catches. If they go down if a predator goes down because of climate change driven changes, for example, that can happen as well. And so those differences actually are more informative, or as informative, I should say, as the synergies between the models. But one of the challenges that we are going to have to overcome is how to summarize that information in a meaningful way when we need to turn this from a research into a sort of advice standpoint. And so I think we're facing that in this next year, and our plan is to do that in collaboration and iteratively with the council, see what they need, what works, and also with other stakeholders. Distribution projections, for example, are something that people are really concerned about or interested in, and that's more on the sort of right-hand side of the suite of models.
Yeah, okay, yeah, thanks. So yeah, it'd be challenging. I mean, finding the common currencies, and they all have different assumptions, spatial, temporal, and so on. So it's going to be tricky, but interesting.
One of the things that we're finding to be extremely helpful in this is those interactive graphic tools. So we're using Shiny. I mean, you can use any number of them, But the ability to quickly toggle between different models and flip switches on and off has become very valuable in that.
Yeah, cool. Thanks.
Shane?
Yeah, I have a question. I just wanted for you to clarify the bottom temperature. Are you this area average over summer?
Yeah, I wonder, Mike, if you can go back. Maybe we can go forward. There's a spatial image. This will work. So the bottom temperature that I was plotting there is survey replicated. And so if you look at maybe the area in 2008, so you can see sort of the shelf edge and the sort of northern extent there. That what we have are surveys that go out on a grid, same place every year, sample for fish, but they also record bottom temperature during that time. So we have in situ observations, but it takes about a month or a couple of months to get from the lower right-hand side all the way across the Bering Sea. So they kind of go in lines. And so what we did for the ROMS model is we used those mean sampling dates at a location and sampled the model on those same dates to see if we could replicate those bottom temperatures we observed. But we also have their weekly bottom temperature, sea surface temperature, and MPZ all for the whole water column. So we have weekly values, and we've been pulling other indices for that as well.
Okay, thank you.
Thank you. Are there any other questions? I have a question. Kirsten, you mentioned combining scenarios, fishing scenarios and climate scenarios. By combining, you meant integrating them, and if so, how? Is that through the socio-economic model?
Yeah, so an example would be, we take the climate-enhanced multi-species model, and we run that model through an MSC loop. So we would have, maybe a better example is to take the EcoSim model as a sort of operating model. This is the reality. We run it forward under projections with different switches turned on, and then we test the climate-enhanced single-species model and the climate-enhanced multi-species model against that. So each year we go forward, we reassess the system. It's not true assessments. You go out and you sample the system, and then you run your assessment. And what this allows us to see is whether or not if there's a systematic bias in a biological reference point. If we're using a B40 or another sort of biological reference point, is that enough to absorb some of, it's designed to absorb some of the climate variability we've seen in the system. Can it absorb that climate? Can it track that climate trend? Another way to evaluate this would be if we did annual assessments versus 5-year assessments, would we still be able to track the change in biomass?